Hello, in this video we're going to prove that the antiderivative of an odd function is even. And this is really spurred on by my previous video when we were looking at the crazy relationships between marginal and joint density functions. And we were integrating an odd function from -1 to 1, which means it's 0, and it dawned on me that must mean that the antiderivatives are even functions. And I thought, oh, let's try to prove that. Anyway, and that's what spurred this video on. It's a little bit different type of video that I put out, but I still think it's a fun video. So the theorem is let f be an odd function. So f of x is equal to minus f of minus x. Then capital F is even, where the derivative of capital F is little f. The proof goes like this. If we integrate f of x dx, take its antiderivative, that's equal to capital F plus some constant, right? Because if you take this derivative, you get f of x back. And note that since it's an odd function, we can take f, the antiderivative of f of minus x is minus capital F of minus x plus some constant called C2. We don't know if those are the same constants yet. Now, since it's an odd function, these two values are equal, and then that means that these two values are equal, right? So if you just replace this in here, you get this. And hence that says that capital F of x plus C1 is equal to capital F of minus x of C2. And this is for all x. So let's let x equal 0, and let's plug it in here and here. But f of 0 is 0, so that implies that C1 and C2 are equal. Therefore, capital F of x is equal to capital F of minus x, which implies that f is even. So this theorem, let's let f be an even function. So that means f of x is equal to f of minus x. Then capital F, the antiderivative of f, in general is neither even or odd. And it just takes one simple example to show that. If little f of x is x squared, capital F of x can be 1/3 times x third plus 1. And this function is neither even or odd, but if you take the derivative of it, you get little f, or x squared. And so that proves this, that it's neither even or odd. Now the last one, if the antiderivative of an even function, f, is odd, then the antiderivative f is such that f of 0 is equal to some constant c. And the proof goes like this. So f of x is equal to this, the integral of f of t dt plus some constant. Right? Now, the integral of, the minus f of minus x is this. So it's minus f of t dt integrated from 0 to minus x. So plus some constant, C2. Now we don't know if these are the same or not. So from this integral, let's let u equal minus t, then du is minus dt, and we get this function here. Right? When you plug in minus x to t, you get x, and you plug in 0, you get 0, and you get this. Now, since little f is an even function, that's the same as you don't need the minus, so it's f of u du plus c2. Now, if capital F is an odd function, that means minus capital F of minus x is equal to f of x. And this is for all x, if it's an odd function. Well, that means if we can plug in any value, let's plug in 0, and these hold. But when we do that, then we're setting this equation equal to this, and those drop out, and that says that C1 and C2 are equal. So let's just call it some constant C. But hence, f of 0 is c. So if we plug in f of 0, this is 0 and we get c. So the theorem is proved. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.